Hi, this is Barrett Givens, and in this video, we're going to introduce the concept of the boundary of a set in a topological space, and then we'll do a couple of examples. So, suppose you have a topological space X with some subset A in it. The boundary of A, which is written as sort of del A or boundary of A, is the closure of A minus the interior of A. So intuitively, if A sort of looks like this, then the closure of A is the smallest closed set containing A. So it's sort of like it comes in and it squeezes A from the outside and it's closed. Okay, so maybe the closed set looks something like that. And then the interior is the largest open set inside of A. So the boundary is whatever's in the closure, but not in the interior. So sort of intuitively speaking, the boundary would be sort of like whatever is like right on the edge of A. Okay. It's not inside, but it's like close to the edges of A intuitively. All right. So let's do a couple of examples. For the first example, let's consider X to be R2 with the usual topology. And let's find the boundary of these two sets. So the first set is a collection of ordered pairs where the first coordinate is between 0 and 1, including 0, but excluding 1. And the second coordinate has the same property. So for the first one, we're going to look at 0 to 1, 0 to 1. So it looks sort of like the I should have made, I'll just make big open circles there. Okay. So includes 0 and does not include 1. So this is an open circle there too. Okay. This is the set capital A for part 1. So what is the closure of A? Well, we've talked before about the closure in R2. So the closure of A looks like the whole square with all edges included. And the interior of A looks like the open set that's contained in there, which is take away the edges. So the boundary of A is just the outside edges. Okay. All right. For the second example, same, still in the R2, but A will be the set of all x comma 0. So all the coordinates, all the points whose second coordinate is 0, and the first coordinate is between 0 and 1. So it's this quantity right there. Okay. In this example, the closure of A is A itself. A is already closed. And the interior of A is empty. So the boundary of A is just A itself. Every point of A is a boundary point of itself. Okay, so that's a couple of examples with R2. Now let's do a couple of examples with the digital line topology. So you may not remember, but the digital line topology is the topology where open sets, the basic open sets, look like either a single odd number or a triple of an odd, even, odd consecutive. Okay. This is not like perfect mathematical notation here, but like a basic open set would either look like 2n plus 1, a single odd number, or it could look like 2n minus 1, 2n, 2n plus 1, three consecutive numbers of the form odd, even, odd. And so one way to think about this set is that a set in the digital line topology is open if and only if, whenever it has an even number in it, it has to have the two odd numbers on either side. Okay? And it's closed if its complement is open. So it's closed if whenever it doesn't have an even number in it, then it can't have the two odd numbers next to it either. So let's see if we can use those sort of ideas to write down the closure, interior, and then boundary for these three sets A. Okay, so for the first one, A is just the singleton 2. Is A open? No. To have an open set, whenever you have an even number, so we have 2 in there, for it to be open, we'd have to have 1 and 3 also in there. So this is not open, and clearly no subset of it is open. And so the interior of A is empty set. I guess that is a subset which is open, but there's no non-trivial open subset. The closure of A, so for the closure, we have to say whenever an even number is not in it, certain things should happen. So the even numbers that are not in it are all the even numbers except for 2. And for each one of those even numbers, the odd numbers next to them are also not in there. And so the closure of A is actually A itself. And so the boundary of A is 2. Okay. So the A is its own boundary. It has no interior. All right. For the second example, let's let A be singleton 5. Let's let A be singleton 5. Well, that is a basic open set. And so the interior of A, because A is open, the interior of A is A, which is singleton 5. Now the closure of A is not currently closed because the complement, for example, the complement contains the number 4, but doesn't contain 5. And the complement contains the number 6, but doesn't contain 5. And so right now the complement is not open. So the closure of A would be 4, 5, 6. And so the boundary of A is the closure, take away the interior. And so that would just be 4 and 6. So the boundary points of a single odd number are the sort of two side-by-side even numbers. All right, and then finally, A equals 0, 1, 4, 5, 9. So we're going to have to use all of the same kind of reasoning here. The interior of A, I need to think of what is the biggest open set contained in A. Well, I can't have 0 in an open set inside of A because if I have 0, I also have to have -1. So we're going to have to get rid of 0. Same problem with 4 because I don't have 3 in A. And there are no other even numbers. So the interior is just 1, 5, 9. And then the closure, what do I have to add to get the closure? Well, 2 is not in A, but 1 is. So I'm going to need to add 2. And 6 is not in A, but 5 is. So I'm going to need to add 6. And then similarly, I'm going to have to add 9 and 10. And so the boundary of A is the closure minus the interior. So the boundary is 0, 2, 4, 6, 8, and 10. Okay. All right. So the idea of the closure, the definition of closure is that it is the definition of the boundary. The definition of the boundary is that it is the closure minus the interior. And so we think of it as the points that are sort of like right on the edge of A. Okay? Thank you so much for listening.